Hello everybody, this video is going to go over the Chatelier's principle. You learned about this in Honors Chem, but we're going to make sure to emphasize some of the key points, some areas where we want to make sure we don't see any mistakes in AP Chem. So if you recall, the Chatelier's principle is what we used when we're trying to decide how a reaction would respond if you stress the reaction or make various changes to the conditions that it's under. When a reaction is stressed or disturbed or changed somehow, the position of the equilibrium is going to change as well. It's going to try to minimize whatever stress you applied to the reaction. Try to undo the problem a little bit. You won't be able to get back to your original equilibrium position. You won't have the same concentrations of chemicals after the stress was applied, but the reaction will find a new equilibrium position where the rate forward will equal the rate backwards. So a couple of practice problems to refresh our memory. So if we have a container that has ice and liquid water in it, and it's in an equilibrium going back and forth, and I raise the temperature, the stress that I've applied is that extra energy. This is an endothermic reaction, so energy is functioning as a reactant. So what has to happen is the reaction is going to try to use up some of that energy to lower the temperature a little bit. It can't get back to where it started, but it can at least be better off than when you came over and messed it up. So in order to do that, the reaction is going to shift to try to make more of the liquid water. We say it shifts to the right, making more of those products. It'll reach that new equilibrium. Once it reaches that new equilibrium, it won't be going in the forward direction more and more and more. It will start going back and forth, just like before when it was at equilibrium. Let's try another one. Here, we're going to add some extra NO2. We're adding some extra product to our container. Well, that's not good. We have to try to use some of that up. So the reaction is going to start going in the backwards direction more, trying to use up some of what you've added. So we say that it shifts to the left to try to use up some of that NO2. It'll eventually get to a new equilibrium position and the rate forward and backwards will become the same again. Instead of adding something, you could be taking it away. What if I have a container that's water and then gas, right, vapor? If I remove some of that vapor, the reaction is going to shift to the right in order to try to replace what I'm taking away. Once it's made some more vapor, then it'll reach a new point where the forward and backward reaction rate is the same. So this works when we take things away, not just when we add things. Works when we change the temperature or the concentration. It will also work if we change the pressure. For example, if we increase the pressure here, the molecules in the container are going to feel too crowded, right? We've now increased our pressure, shrunk that volume down, so they're too close together. So in order to relieve some of that pressure, the reaction is going to proceed in whichever side will combine particles together to result in fewer moles of gas present. Because the fewer particles that are present, the less pressure it will be feeling. So you can see on this example, the left has 1 mole of gas and the right has 2 moles of gas. So when you increase that pressure, the reaction will shift towards the left, fewer moles of gas are on that side. So just showing you here in a little more detail, right? You got 4 moles of gas here in this example. You have 2 moles of gas on this side. So if you increase that pressure, you would want to move to the right-hand side you're going to feel way less crowded with only 2 moles of gas present. Doesn't matter what type of gas it is, right? It's okay that these were 2 different types. All we care about is the overall number of particles. We don't care if there are solids or liquids or aqueous. We're just worrying about the gas here because that's the type of particles, the phase that would be affected by a change on that pressure. So we're only interested in gas particles for this type of problem. That's a common mistake we see is people will count all the moles of substances, but not just the gas ones. So be a little bit careful there. And it works going the other way too. If we lower the pressure, we raise that volume up, now those particles are too far away from each other. They're not crowded enough. So this time it's going to shift towards the left to try to make more gas to fill up all that empty space, to find that new equilibrium position. I want to show you some graphs that are really, I think, try to emphasize the idea that we're reaching a new equilibrium, that we can't go back to where we started. So if we have this reaction here, and we add some extra N2O4, what ends up happening, you see, like we dumped a whole bunch into the container. Well, that's not good. It wants to use some up. Some of it will decompose and turn into NO2. So you can see on the red line, the amount of N2O4 will go down a little bit, while the amount of NO2 goes up a little bit. Now, we were not able to reach our original starting position for the N2O4, were we? We weren't able to get all the way down to our original concentration. But is this place here at least a little bit better than the high point? Sure. So it's a little bit better. And you can see the concentrations level out. They're no longer changing. They've reached a new position where the forward and backwards reaction rates are the same. Not the same concentrations as each other, not the same concentrations as where we started, but we finally reach a new equilibrium position. We're back to the point where Q equals K, but not back to where we started. We can see this if we add some more NO2. This time, look at the blue line. We dumped in a whole bunch more. Some of it gets used up, which is great. In the process of using up that NO2, we end up making more N2O4. We don't get to go back to where we started. We have a new equilibrium position, but it's at least better than it was. We finally are back to a point where the forward and backward rate are the same, not the same concentrations as before. One last thing I just want to point out, a quick reminder, you should have learned this in Honors Chem, but sometimes I've noticed this is one of the most common mistakes, and I think the reason this next part is a common mistake is because people often mix up kinetics and equilibrium. We always teach them really close together, one after the other, because they're related, but you have to be careful with how you talk about catalysts. If you remember, a catalyst provides an alternative to the original mechanism. It's a more efficient mechanism. It will have a lower activation energy overall than the original one. That's why it can go faster. Key thing to understand is that the catalyst speeds up the forward and the reverse reactions. It's not a one-way street here. It speeds up both of the directions. And because it's speeding up the forward and the backwards direction at the same time by the same amount, it's not actually going to change the ratio of concentrations that you have when you're finished. So you're not going to end up with a new equilibrium position. All that's going to happen is you will get to equilibrium faster. That's a really key thing to understand. So sometimes we'll ask you which of these factors can affect the equilibrium position. Don't fall for it, right? They're trying to trick you. They want to make sure that you understand that a catalyst will speed up the reaction, but it doesn't change the ratio of chemicals that you have when you're finished, right? You're going to end up at the same equilibrium point, just faster. There's a really funny cartoon that shows this, okay? I don't know if you're familiar with The Simpsons or not, but it's a kind of a funny cartoon picture here. So trying to emphasize you don't change your positions, you just get there faster. So in this silly graph, our starting point is that he's hungry and he's trying to get fed. And in each of these scenarios, we are starting and ending at the same places. It's just a matter of what route do we take to get there. So if you're going to cook your own food, I mean, that's a lot of time, that's a lot of effort, that's a lot of energy trying to cook your own food. Or the alternative mechanism is that you order takeout. And so you have to maybe decide which restaurant, which is a little bit of effort to decide. Then you got to decide what to order, which is a little bit more effort too. Then you got to actually pay for it. You see, it's a different mechanism, but each of these steps is easier than having to cook it all by yourself, right? So just a silly way to try to remember this key thing that they love to try to trick you on. Okay? Well, that's it for this lesson. I hope that was helpful. Bye.